Radioactivity was discovered by French physicist Henri Becquerel in 1896, but it took Marie Curie's groundbreaking and systematic study of radioactive materials for scientists to begin to understand the mechanisms behind nuclear decay. By the way, if it seems like there's a lot of chemistry in nuclear physics, you would be right. In fact, Marie Curie was not only the first woman to receive the Nobel Prize, she remains the only person to have received the Nobel Prize in two different scientific fields, both physics and chemistry, and that's because it required her special expertise in both fields to study nuclear decay. Light as a form of electromagnetic radiation was studied extensively throughout the 1800s. Visible light, of course, was a popular subject of study, and radiation at wavelengths close to visible light were discovered in 1800 for infrared and 1801 for ultraviolet. In 1887, Heinrich Hertz created radio waves in his investigation into Maxwell's predictions of electromagnetic waves, and X-rays were discovered in 1896, again during the course of experiments involving electromagnetism. In 1897, however, a form of radiation was discovered by Henri Becquerel that was not the product of direct electromagnetic experimentation or studies involving visible light. This type of radiation seemed to be spontaneously emitted by certain minerals through some mechanism that flew in the face of the scientific understanding at the time. Becquerel's student, Marie Curie, adopted the new phenomenon as her PhD thesis. She dubbed this phenomenon radioactivity. By 1900, 3 basic types of radioactivity had been identified, although the nature of each type was not understood. They were therefore simply named after the first 3 letters of the Greek alphabet: alpha radiation, beta radiation, and gamma radiation. There is also a 4th type of nuclear radioactivity, neutron emission, which was not discovered until the 1930s. We're going to start with gamma radiation because I think that is the simplest to understand. By 1914, gamma rays had been established as just another form of electromagnetic radiation, as they had been observed reflecting and refracting, just like other types of visible and non-visible light. As a type of electromagnetic radiation, gamma rays are actually just photons, and when the standard model of particle physics was established, the gamma symbol was adopted for the photon. Gamma rays, however, usually refer specifically to very high-energy photons, with very short wavelengths that allow them to penetrate materials like clothing and skin. As the force carriers for electromagnetism, they are also very good at ionizing particles within the body by stripping charges from molecules and atoms. The combination of higher energy, high ionization effects, and high penetration make gamma rays quite dangerous, although they have also been harnessed for therapeutic treatments when carefully directed. In module M5.3, we talked about how atoms can absorb light with certain wavelengths, leading to certain objects appearing to have color. When light is absorbed by an atom, a photon transfers its energy to an electron orbiting the atom, which bumps the electron to a higher energy level, a less negative potential energy, as we saw in module M5.2. But the reverse can also happen. An electron that starts in an excited state can also transition back down to a lower state, emitting a photon that has precisely the difference in energy between the 2 electron energy levels. Again, only certain orbits are allowed for electrons, which means that only photons with specific amounts of energy will be emitted for a given type of atom, corresponding to the available electron orbits. Since this is just the reverse of what we did in Unit 4 with the absorption of light, we can use the exact same equations, only now, since we are doing nuclear physics, we will also want to use nuclear units. So for the value of Planck's constant times the speed of light, hc, instead of using joules times nanometers, we're going to translate that into nuclear units, and we're going to use electron volts times nanometers instead. The value of hc in nuclear units is just 1240 electron volts times nanometers. We can then calculate the wavelength of the photons that are emitted for particular atomic transitions. Let's calculate the wavelength of a photon that is emitted when an electron transitions from the 3rd energy level of hydrogen at negative 1.512 electron volts to the 2nd energy level of hydrogen at negative 3.401 electron volts. First, let's find the energy difference, E3 minus E2. We then divide hc by 1.889 to get the wavelength of the emitted photon at 656.432 nanometers. This wavelength is in the visible spectrum and corresponds to a shade of red. So if we could capture all the light from photons being emitted by a large sample of hydrogen atoms, we should see a large number of red photons with a wavelength of 656 nanometers. Well, it turns out that physicists, chemists, and biologists do exactly that. They capture the light emitted from various substances and plot the wavelengths they find. In the case of hydrogen, many of the photons will be in wavelengths that are not visible, but there are 4 distinct lines that are in the visible spectrum: 2 purple, 1 blue, which is also called cyan, and a red. The electron energy levels of hydrogen are unique to hydrogen, so the specific combination of wavelengths that are emitted or absorbed by hydrogen is kind of like an elemental thumbprint. If you see this particular pattern of lines on a spectral plot, you know that you have some hydrogen in your sample. Spectral plots can also be made based on what wavelengths hydrogen absorbs. Since the hydrogen levels are the same for both absorption and emission, the 2 spectra are essentially the reverse of each other, with black lines at 656 nanometers and the other typical hydrogen wavelengths that show the wavelengths that were absorbed by hydrogen. Shown here are the atomic spectra of some larger nuclei. Larger nuclei have more energy levels, and therefore they have a lot more transitions, so their spectra are more complicated but still unique. This is how astronomers can determine the chemical composition of distant stars. Spectroscopy can also be used to determine the chemical makeup of complicated molecules and unknown substances. When an electron transitions to a lower energy orbit and emits a photon that then escapes the nucleus, it is called gamma radiation or gamma decay. The nucleus itself does not change during gamma decay. The number of protons and neutrons remains the same, and the elemental properties of the nucleus remain the same. So to denote a nucleus in an excited state, the elemental symbol is written with a star or an asterisk. If the energy of the excited state is known and the energy of the ground state is known, the energy of the released photon is just the difference between the 2 energy states. Some isotopes of iridium can absorb ambient light relatively easily, resulting in iridium atoms that frequently have electrons in excited states. Iridium can therefore provide a fairly consistent source of gamma radiation. This radiation can be used for radiation treatment in cancer patients. Before the damaging effects of high-energy radiation were well understood, some watches actually had radioactive paint on the dials to make them glow in the dark. Ambient light during the day puts the molecules in the paint into excited states, and then at night or in the dark, the paint undergoes gamma decay, emitting gamma radiation or photons to light up the dials and the numbers on this watch face. These days, glow-in-the-dark watch faces and other glow-in-the-dark items are made with much safer chemical compounds. Next, we'll talk about beta radiation or beta decay. Beta decay is one of the primary demonstrations of the weak force at play. In fact, beta decay led to the discovery of neutrinos, the only fundamental matter particles that do not interact with the much stronger electromagnetic force. In M5.1, we talked briefly about how the weak force can change a down quark into an up quark, so that a neutron can actually turn into a proton, emitting an electron and an antineutrino in the process. When this process happens inside a nucleus, and an electron and an antineutrino are emitted, it is called beta decay or beta radiation. When beta radiation was first being studied, neutrinos had not been discovered yet. Scientists knew enough about electrons to detect them, but the big mystery was what happened to the energy. They found that the amount of energy that the nucleus lost was always more than the amount of energy they measured in the electron. Conservation of energy requires that the extra energy had to go somewhere. So in 1930, physicists theorized that there was some other particle being emitted that did not interact with the electromagnetic force. However, detecting this other particle that doesn't interact with the electromagnetic force proved difficult. In fact, many famous nuclear physicists, including Niels Bohr himself, were ready to give up on conservation of energy and just say that energy is not conserved in beta decay, rather than believe in the existence of a nearly impossible to detect particle. 26 years after the neutrino was proposed, it was finally detected and confirmed, and conservation of energy was saved. A similar process can also change a proton into a neutron. When this happens, a positron and a neutrino are emitted instead of an electron and an antineutrino. When an electron is emitted, it is called beta minus decay, and when a positron is emitted, it is called beta plus decay. You may see some websites that still just refer to an electron or positron as a beta particle and ignore the neutrino. Notice that in beta minus decay, a neutron is turned into a proton, so the element shifts to the right on the periodic table, in this example from carbon to nitrogen. In beta plus decay, a proton turns into a neutron, so the element shifts to the left, in this case from carbon to boron on the periodic table. The reverse of beta minus decay is also possible. An electron that is orbiting around a nucleus can actually be absorbed by a proton, turning it into a neutron. This is called electron capture. Usually, however, neutrons are more likely to decay into protons than the other way around. So the most common form of beta decay is beta minus decay, where an electron and an antineutrino are emitted, followed by beta plus decay and electron capture. The reverse of beta plus decay, or positron capture, is not really possible for two major reasons. First, positrons are strongly repelled by the protons in the nucleus, so they don't usually get close enough to be captured. Second, even if a positron did get into the nucleus, it would have to navigate through the electron cloud, where it is far more likely to be annihilated by an electron than to make it all the way to the nucleus in order to be captured. The total energy carried away from beta decay is shared between the neutrino and the electron, or the positron for beta plus decay. But there is no way of knowing how this energy will be distributed. It is a quantum mechanical probability, and we don't know what the final result is until we actually measure the energy of the electron or the neutrino. This plot shows the energy distribution for an electron emitted in the beta decay of carbon-14 to nitrogen-14. The y-axis shows the probability that an electron produced in this decay will emerge with the energies along the x-axis. So about 18% of the time, electrons released in this reaction have a kinetic energy of 0.06 MeV, and their associated neutrinos have a kinetic energy of about 0.1 MeV. The mass of the carbon-14 nucleus is greater than the mass of the nitrogen-14 nucleus, so the total energy of the electron plus the neutrino is equal to the lost mass, converted into energy via E equals mc squared. Just be careful. Usually tables of elemental properties give the masses of the entire atom, including the mass of the electrons that orbit the nucleus in the ground state. Since the beta decay products only carry away the difference in masses of the nuclei of the atoms, calculating this energy difference requires you to carefully subtract the masses of the orbiting electrons from the masses of the atoms. I won't require you to do that in this unit. The third major type of nuclear decay is alpha radiation. In alpha radiation, a small chunk of the nucleus actually breaks off and is emitted as a particle. Alpha particles are actually just helium nuclei with 2 neutrons and 2 protons each. This means that the initial nucleus, often called the parent nucleus, has 2 more neutrons and 2 more protons than the final or daughter nucleus. In alpha decay, the net number of protons and neutrons on each side of the equation remains the same. So unlike in beta decay, we don't have to worry about converting masses. This allows us to just consider the total energy. Total energy should be conserved on both sides of the equation, so let's tally up the kinetic and potential energy on each side in this example, which shows the alpha decay of uranium-238 to thorium-234. On the uranium side, we just have the potential energy of the uranium nucleus. On the decayed side, we have the potential energies of both the thorium and the helium nuclei, plus the kinetic energy of the helium nucleus that is emitted as radiation. Recall that the potential energy of the bound states of nuclei is negative. The binding energy of each nucleus is the energy required to keep the state bound, so it equals the potential energy, but the binding energy is positive. Since we can usually find the binding energies from tables of elemental data, let's rewrite this in terms of binding energies. The kinetic energy of the helium atom is just the energy released by the alpha decay. We can then rearrange this to solve for the energy released. Right now, we only have one initial nucleus, but I'm going to go ahead and write this equation as a sum over both the initial nuclei and the product nuclei because we will be seeing this equation again when we talk about fusion. Now we can plug in the numbers for binding energies to actually find the energy released in this particular reaction. Notice that the daughter nucleus, thorium-234, has a higher binding energy per nucleon than the parent, uranium-238. This means the daughter particle is more stable than the parent particle because it is bound more tightly, and that's why the parent particle will decay in the first place. One very common mistake that students make is to try to find the difference in binding energy using binding energy per nucleon instead of the total binding energy. Because the 3 nuclei all have different numbers of nucleons, this does not work. So the first thing we have to do is make sure we are using total binding energy for each of the elements involved. Then we just plug the total binding energy in for each nucleus into the equation and find that the released alpha particle has an energy of 4.3 MeV. The last type of nuclear decay is neutron emission. Neutron emission can occur when an atom has an excess of neutrons. For example, when an element undergoes beta decay and a proton turns into a neutron. Then if there's an excess neutron, it can be shed via neutron emission. However, neutron emission is most common in association with fission, which we will talk about in the next module, so we won't go into it in depth here. In the early days of the study of nuclear radioactivity, it was believed that atoms just consisted of protons with electrons orbiting around them. Physicists did not realize that there was another neutral particle involved in the nucleus as well. However, experiments began showing signs that nuclei were decaying into a daughter nucleus and some other particle that was not a photon and that didn't have any charge. These neutron emission events led to the discovery of the neutron in 1932. In Module M5.1, you learned that quantum mechanics describes every process based on probabilities that certain interactions will occur, as opposed to the deterministic cause and effect relationships described by Newtonian mechanics. Nuclei are on a small enough scale that the probabilistic nature of quantum mechanical rules cannot simply be averaged out and ignored. So it can't be determined precisely when a particular nucleus will undergo decay. Instead, the timing at which a particular decay will occur is dependent on the quantum mechanical probabilities associated with each of the processes involved. If the probability of the process is higher, the decay is more likely to happen quickly. If the probability of the process is very low, it might be some time before the decay happens. As an example, if you're rolling a die, then you have a 1 in 6 chance of getting exactly a 6, but you have a 5 in 6 chance of getting anything other than a 6. So if you roll the die many times, you will probably get something other than a 6 much faster than it will take you to get exactly a 6. However, if we take a large sample of a particular radioactive substance with many nuclei that might decay, the probability of each individual nucleus decaying can be averaged out to find a decay rate for the sample as a whole. The decay rate is the number of nuclei that decay per second. Notice that this makes the units for the decay rate 1/seconds. At first, when the sample is large, there will be many nuclei available for decay, so the number of nuclei that decay per second from the sample will be large. But as time goes on, there are fewer and fewer nuclei left that are still available to decay. Thus, the number of decays per second will decrease over time, meaning that the decay rate itself decreases over time. We call the initial decay rate R0, and then we can find the decay rate at any given time using the equation R of t equals R0 e to the negative lambda t. Lambda here is the decay constant. This is the probability that any particular nucleus will decay at a particular time. Be careful not to confuse this lambda with the lambda that we use to represent wavelength. This equation might look vaguely familiar to you. That's because it's actually the exact same form of the equation that we used for discharging a capacitor, where the decay rates take the place of charge, and 1/RC, the time constant, is now replaced by the decay constant. The good news is that there is only one decay rate equation. We don't have to worry about charging radioactive nuclei back up. This also means that the math that you learn to calculate the charge of a capacitor sometime after it starts discharging will also serve you here. Let's do an example. Suppose a radioactive sample is initially decaying at a rate of 5 counts per second. How long will it take before the decay rate is 4 counts per second, if the decay constant for this substance is 0.028 inverse seconds. To solve this, we are given that R0 is 5 counts per second, and that R of t, for the time that we're trying to find, is 4 counts per second. Plugging this in, we have 4 counts per second equals 5 counts per second, e to the negative lambda times t. We can do some algebra, and then take the natural log of each side using the same relationship that we used for capacitors. Do a little bit more algebra, and we arrive at our answer. The decay rate will be 4 counts per second after 7.97 seconds. The decay rate is just the number of radioactive nuclei present times the probability that a given nucleus will decay per second. So we can relate the decay rate, R, to the number of radioactive nuclei present, N, through the simple relationship R equals lambda N. This allows us to write a formula to calculate the actual amount of a radioactive isotope still present in some sample at any given time. Let's do another example, this time using the amount of the substance present. We aren't actually given the initial amount N0, and we're not given the amount at the time that we're looking for. But we do know that N of t is exactly half of N0. We do some algebra and we find that half of the substance has decayed at 21660.8 something. What unit should we use here? You may remember that with capacitors, the time constant, 1 over RC, had units of 1 over seconds. That way, the time constant times the discharge time in seconds was a unitless quantity. Well, the quantity in the exponent always has to be unitless. So if we are given a decay constant in minutes, we know that the time elapsed, t, must also be measured in minutes. So our answer is that half of the substance has decayed in 21660.8 minutes, or about 15 days. The time it takes for 1/2 of a sample to decay has a special name called the half-life, and we give it a special symbol, tau with a subscript of 1/2. Often, instead of quoting the decay constant, the half-life will be given instead. We already found that the half-life equals the negative natural log of 1/2 over the decay constant, regardless of what the initial amount of the substance is. We can simplify this further by noting that the negative log of 1/2 equals the positive log of 2. So a simpler equation for the half-life is given by the half-life equals the natural log of 2 over the decay constant. Knowing the half-life can be useful to quickly figure out how long it takes for a sample to reach 1/4, 1/8, 1/16, or smaller fractions times the original amount present. For example, it takes 2 half-lives to get 1/4 of the original sample. So if you multiply the half-life by some integer n, then that gives you 1 over 2 to the n for the amount of radioactive substance still present. In this module, we talked about the 3 main types of nuclear decay. We talked about alpha decay, where A, the total number of nucleons decreases by 4, and Z, the number of protons decreases by 2. The alpha particle released is just a helium nucleus which carries away 2 protons and 2 neutrons. The alpha particle has a kinetic energy, E released equals the sum of the binding energies of the products minus the sum of the binding energies of the initial nuclei. We also learned about beta decay, where A, the number of nucleons stays the same, but Z, the number of protons, increases by 1 for beta minus decay, or decreases by 1 for beta plus decay. The beta particle is just an electron plus a neutrino. The third main type of nuclear decay is gamma decay. This one doesn't change the nucleus of the atom at all, so A and Z stay the same. The gamma particle is just a photon, and its energy is determined by E equals Planck's constant times the frequency, or Planck's constant times the speed of light divided by the wavelength. We then talked about decay rates. Both the decay rate and the remaining amount of a radioactive sample decrease exponentially through 2 very similar equations. R of t equals R0 e to the negative lambda t, and N of t equals N0 e to the negative lambda t, where lambda is the decay constant. The half-life of a radioactive substance is related to the decay constant by the equation tau 1/2 equals the natural log of 2 over the decay constant.